So let's find the temperature distributions. Temperature distribution. So first case is plane wall, but for finding temperature distribution we have to make a lot of assumptions. Right, the same assumptions are there, like one-dimensional heat flow for plane wall, and for cylindrical and spherical body radial heat flow, steady state, no internal heat generation, material is homogeneous in isotropic, both the surfaces are maintained at different temperatures. All these assumptions are same except one assumption, which is the thermal conductivity variation with temperature. Right, before this we assumed that thermal conductivity is constant within the given temperature range, but here we said that K value varies linearly with temperature. All the other assumptions are same as previous. Right, just remember that. So for case of plane wall, let's say right, we have to find the temperature distribution when the thermal conductivity varies with temperature. The same setup we're talking about. There is a plane wall, its surfaces are maintained at two different temperatures, there is no internal heat generation, steady state. Right, this is x equal to 0, x is equal to L. Right, start with Fourier law. K is equal to minus K A dt by dx. Since it is a plane wall, A is not varying with temperature, A is not varying with x. This is the x coordinate. Okay, so it is constant, but K is not constant, so we have to plug in K naught 1 plus minus beta T A dt by dx. So integrate it from x, from 0 to x, and on the right hand side K naught A will be coming out of the integration, and inside the integration will be 1 plus minus beta T dt, and it will be integrating from T1 to T. Right, solve it. So Q times x equal to minus K naught A times T plus minus beta T square by 2, putting limit T1 to T. So after putting the limits, you will get like Q times x equal to minus K naught A T minus T1 plus minus beta by 2 T square minus T1 square. Right, take T minus T1 as outside, Q times x T minus T1. Taking T minus T1 as constant, inside it will remain 1 plus minus beta by 2 T minus T plus T1 will be left. Right, take this as 1, Similarly, if we integrate from x equal to 0 to x equal to L, we get equation like q times L, because we are integrating from x equal to L, x equal to 0 to x equal to L, minus k naught A, and it will be T2 minus T1. Okay, so this we get when we integrate from x equal to 0 to x equal to L. T2 plus T1. Right, so this will be the equation 2. So dividing both the equations, we can find the temperature distribution. T minus T1 divided by T2 minus T1 x by L. So similar type of temperature distribution were coming for steady state, right, for plane wall when there was no heat generation and also thermal conductivity equal constant, right? But here extra term will come because of variation of thermal conductivity with temperature. So the extra term is 1 plus minus beta times T1 plus T2 by 2, and 1 plus minus beta times T plus T1 by 2. Right, so this will temperature, if beta is 0, then you can see that this term will be 1, this ratio will be 1, right? So T minus T1 is equal T minus T1 by T2 by T1 equal to x equal to L. So for the case of that we have done previously, right? And if you want to find the heat transfer, you can find like this: T1 minus T2 divided by L okay, divided by k naught 1 plus minus beta times T1 plus T2 divided by 2 times A. How I have got this equation? From this, right? After rearranging, we can find this, and we can see what is this. This term is nothing but k average value, right, as we have find here, right? So we can write like q is T1 minus T2 divided by temperature difference divided by thermal resistance L by Ka, and K in this case will be K average times A, right? So try this same thing for hollow cylinder and hollow sphere. I will show you the results in the next lecture. Thank you.